Hello, can you hear me, guys? So, good evening, all of you guys. And I am trying something new with this new streaming and stuff. So, I sort of displaying it to you. So, it's introduction, guys. So this is our channel. So, I'm really excited since I am doing this live for the first time. With in our channel of Cheenta Statistics Department. If you haven't subscribed in this channel, please do. Okay. So we are trying to make this YouTube channel a really grandeur success. Okay. So good evening, all of you guys. Hi. So yeah. So let's start now. Hi, Richa. Okay. So who are all here? Devargo, Hemant, Gagandeep. Hi, Ishan. How are you? Raj. Is Shayul here? I don't know. Okay. Hi, Aniruddha. Hi. So, okay, so tomorrow our Bose Olympiad starts. Sorry, not Bose Olympiad. I mean, the registration completes today of MN Satsi. So, let's see. Hi, Shayul. So, welcome to Cheenta. It's the first statistics class, or not a first estimation class. Shai should play the video once again for you. Okay. Good evening. Yeah, so I'm doing live streaming, so it's really good. And let's start, okay? Hi, Sahiti. I think it's a first class of mine with you. So let's make it good. Okay. So let's start. So what's on my mind today? We will start estimation. And in case you haven't subscribed to this channel, please do subscribe. Estimation theory, okay? So let's see what we have on our mind. Can you see? Can you see the board, guys? Shayul, can you see the board? So what is statistics all about? So many people are from math background. So I think they should take this opportunity out to understand the statistics and the inferential, the probability aspect. So what we essentially do in statistics, you should understand this. We form opinions about the whole population, okay? What opinions? So suppose you are a student, okay? So for example, take the example of schedule, okay? So schedule is new to this class, and we have a population of like our population. So what schedule is looking for? Schedule is looking for how good or bad we teach statistics, okay? That's the population. So what we have planned to give schedule a trial class, which is sort of a sample. Okay. And that sample, using that sample and idea and the data, schedule will sort of assume the population of the actual level of classes that happens in Cheenta. Okay. So this is a real life example of how population and sample are playing a role in this Cheenta classes itself. So population is the actual sort of classes we take or we are going to take in the future. And the trial class is sort of the sample that I'm offering to the new students. For example, schedule and others. Okay. Or for example, Saidi will understand from my class today how teach whether I am suitable for her or not. Okay. So simple idea. So now there are two aspects. So essentially what we're trying to do, we are trying to infer about the population, about the classes we take from the single trial class or samples of trial class. Okay. That's the essential idea. Now, so the idea is that suppose Shairul is trying to understand how long we take the classes. Okay. So the random variable here is how long we take the classes, the length of the classes. So Shairul comes up and I will say the length of the classes follows a normal distribution with mean 1.5 hours. We can tell this, right? The length of our classes follow normal distribution will mean 1.5 hours. So that is our mean. So Shairul doesn't know this mean, okay? So he wants to understand this mean. So take this example now. So take our classes. So Shairul is new today here. So what I am giving a trial class. So it's a demo. So demo class length. So Shairul's understanding, what he's trying to understand is the demo class length. Okay, it's a random variable following normal some mu. Okay, with some standard deviation say of 5 minutes. Okay. So this is the idea we are trying to understand. So now Shairul, I hope you are understanding. So what Shairul is trying to understand is that what is this mu? Okay, he may ask me, okay, Sujit sir, what is the mu of your class, or what around what time it is your class length is. I will tell him that okay, I will give you a demo class. Please check it out instead of telling 1.5 hours. Okay, Shairul comes up here, and suppose instead of one demo class, I decided to give him 5 demo classes. Okay, that is a D1 length. So it's some. So I'm assuming this model. Okay. So D1 length is sort of a representation of this model. It's a sample from this model. And then we take him D2 and D3 and D4. Okay. Shairul, so I hope you're understanding. So now based on this data, he is going to understand that what is the average length of the classes. What is the mu over here? He wants to understand the mu, which he should get around 1.5. He should not get exactly 1.5. It should get around 1.5. So essentially, this is the idea of the property of inferential statistics, a part of the inferential statistics. So from population to sample, what we did, we assumed a probability distribution, that is x follows some normal mu comma sigma square, or say 5. And from sample to population, what we will know, what we will understand is, what we will learn today or from today is the inferential statistics. Okay, the estimation part and the statistical part. That what is the idea, like how can we infer about the population? We can ask, okay, so I suppose Shairul, I told Shairul, say Shairul, so 2 type of questions that Shairul can ask. I tell Shairul that Shairul, our class is of 1.7 hours. Okay, and Shairul does the demo classes D1, D2, D3, D5, and he can ask, okay, is the class mean length really 1.7 hours? So that's the testing a hypothesis problem. Okay, that's the first type of problem. Second type of problem. First type of problem is that trying to understand from the data what exactly is a good estimate of mu hat. Okay, this estimate of mu hat, we will actually this hypothesis is true or not. So these are the two central idea, that whether what I'm thinking about the population is true or not, and what is the estimate, what is the idea of the parameters of the population. Okay, all of you can understand, guys? Any doubts? So I gave you a real life example based upon how the statistics that's actually happening in our mind. Okay, the whole business world is actually doing this statistical terms. This is all about data analysis. Okay, so what is the probability step? So we assume that the population actually follows some probability distribution. This is called parametric inference, parametric statistics. So we are assuming some parameter based on that. There's something called non-parametric statistics too. Okay, we are not going to deal in this MStat preparation. The parametric statistics are actually all about this idea of parameters and understand modeling the population with some probability distribution. Okay, any doubts, guys? No. See, to understand whether the hypothesis is true or not, we have to find a suitable estimate. We will see that procedure. But I'm telling about the questions that you should ask the statistician in the making. Okay, the question you should ask yourself, that what exactly is what we are doing it. So we are modeling the population with a probability model, that the length, what is the population over here? Let's try to understand the population. The population here is what? Is the length of the classes, right? Now I take a sample. Now we assume the length of the classes follows some distribution. That is called that is where the probability distribution comes up. We assume it follows some probability distribution, okay? And then we take a sample out of it. We take a small sample out of it, that is the demo classes that we are offering to the students. Say D5, 5 classes I give to Shariul. Shariul, please don't ask for 5 classes. We have only 1 demo class. This is for demonstration purpose, okay? Okay, so we give 5 demo classes, and then based on that we try to infer about the length of the classes. Okay, so we have a parameters over, since we are assuming a distribution, we don't know about the parameters, right? If we know about the parameters, there is no need for a demo class. We will suppose Shariul is, or say suppose Prabhat. Okay, Prabhat is suppose Prabhat wants, is also in same years of yours, and he wants to enroll in Cheenta classes. Okay, he's a student come intern. Example of Prabhat. So he knows everything out of the demo length, because we discuss together what is the length. He knows the parameters, right? So he will not require a demo class. He knows the parameters itself. But take the example schedules. He doesn't know about the parameters. So he want to estimate the parameters to know about the distribution. Because we know that suppose I have a emergency, okay, and I have some homework or some discussion with my professor or some PhD guide, to be PhD guide and master's is whatever. So in that case, I will end the class quickly, or I'm excited for like today to tell you a new topic, to discuss a new topic with you. So I will extend it by 10 minutes. So it is a random variability. We don't know it, but it's around a mean. Okay, it has a basic structure, the basic central tendency. That is the mean. So there are parameters. That's why. And based on the parameters, the sample idea is that the sample, using the sample now, we will use inferential statistics to get back to the parameters. That is the distribution, the whole how it is distributed. This is the central idea of statistical estimation. Okay. All of you understood? Any doubts, guys? Yeah, exactly, Gagandip. You're right. You're right. See, it makes sense, right, Gagandip? That's all what we do. Okay, why do we ask for testimonials? Okay, suppose some student comes up to me, and that student asks that how many students have got ISI MSET from your place. So what essentially that person is trying to do? That person is trying to check or get some data about us and trying to infer about the population. For example, Hemant is going to run a business. Okay, so he have to give testimonials on his website. Why he has to give testimonials? Because that sort of makes sense, gives an idea of the data that we can tell to the students. Okay, they're collecting data and they're sort of inferring about about the parameters of the Cheenta statistics department. Okay, this is the entire idea. Now, what is the prior distribution? That is a different aspect, but this is the whole philosophy of estimation and statistics. Okay, I hope it really resonated with you, since I made this like a real life example since you're taking the classes. Sahiti, I hope you understood. And what about you, Shayul? You are the focus of the discussion today. I hope you didn't mind. I mean, thanks for coming, because without you, the example wouldn't have been so lively. Yeah. Okay, good. So now, what's the next step? You can see from the screen that we have two common types of statistical inference, as I have told. So we first estimate the parameters, one type, and we sort of guess a null hypothesis about the parameters. Okay. For example, Shariul will understand or ask whether the mean of the distribution, mu of the length of the class is really 1.5 hours. That means I am telling the truth or not. Okay, that's simple. Okay. Now there are two forms of estimation. One is point estimation. For example, a single value. Okay. Or I interval estimate. Say 1.4 hours to 1.6 hours. Okay. This is the idea. Okay. So this is we will now form the what is essentially the next step. We will form the steps and the algorithm. So so let me give an example. Okay, so I hope everything is clear with you. We are ready to set ahead. So the whole idea of statistical inference is to create the mathematics using the probability models to get to the perfect estimate. That's it. Simple stuff. Okay, there is no hi-fi deal over it. Just the basic mathematics you need to know to get over it, to get to the estimates of the whole thing, and then building up the mathematics of the premise of the whole idea. Okay, nothing hi-fi about it, but it's really simple and really beautiful and really intuitive. That's the best part. Okay, so before I move ahead, okay, so let me give okay, so let's move ahead to the next stuff. Anything to tell over here? I don't think so. Yeah, so remember this, then you will understand everything. Okay, nice. Okay, chalo. So now what's the first step? I will revise an example that you already done below in our classes, maybe. That is a simple linear regression. Okay. Okay, I should not rub this, otherwise it should make sense. Okay. So let's do some revision stuff. Thanks to Gagandeep, I've really become very confident in Google Gem, and I'm thinking to use it permanently for YouTube lives. So yeah, congratulations to Gagandeep's idea. Okay, so revision stuff. So what is the revision stuff? What we have done, let's see. So we have done this sort of idea. So we in regression, so the idea is that, let's get back to regression, okay? So I'm just doing simple linear regression to make you understand. So remember what was yi? You remember yi was normal follows normal mu plus, sorry, beta naught plus beta 1 xi comma sigma square, right? So this was the normal essential idea, right? Now, remember how we approached it? We approached in a very specific manner. And it's actually relevant in the field of machine learning also. It's actually how it's called it. And it's same in statistics too. Both are brothers and sisters. So, first what we do, what is our aim now? Our aim is to get an idea about what? About beta naught and beta 1, right? So what are the steps we follow? We follow the model. This is a basic model. And then what we did? We took the least square estimate, the loss function, okay? And we took the minimization of it. We minimized it. Okay? And by minimization, we got the parameters. Simple stuff. So this is an algorithm. Okay? And then what we did? We did the inferential part, that how good are the estimates. See, inference not only tells you that the estimate, but they also tells you how good are the estimates. And we did that by MAC, right? So we will revise everything together in this aspect also. This was the algorithm. So therefore, what is the step of mathematical, the estimation part, the theory of estimation, we have a model. Okay, that yi follows some f of theta. Okay, and then we will have some algorithm. Various algorithm will give different outputs. Algorithm, okay, and by that algorithm we will get some output, some theta hat. Okay, that is an estimate of theta. So the idea of estimation theory is to give you various algorithms. The first part, various algorithms. Okay? So today I will discuss 3 such algorithms. First algorithm you already know, that is a least square estimate. Okay. The second algorithm was that is only relevant for regression, okay? Not in general cases. The second is what? The second is the method of moments. These are all algorithms, okay? The algorithms to get to the estimate. And third is, now next part will be understanding how good of the estimate. That's where comes the sufficiency part. That's where comes the consistency part in the theory of whole statistics, okay? Understand whether it's good or not. Okay. Now method of moments, maximum likelihood estimator. Okay. So these are the ideas. So we will do this algorithms one by one. We already know this. We will do this maximum and maximum likelihood estimator first. Okay. Okay. Any doubts, guys? Any doubts? Okay. Great. ठीक है. चलो. So let's do the next part. ठीक है. चलो. Nice. So let's build a mathematics slowly, okay? So we will build everything clearly in a very systematic way, okay? Let's do it. So I will take examples from books only, okay? From John and data analysis, but I will make you understand everything over here, okay? So for example, so I have thought of making a real life data with you, but since I have my meeting with my master's professor for master's thesis, I couldn't make that data. I would make a video on it soon. So what I was trying to predict. So this was the idea. So Virat Kohli's score I was trying to do. So we want to sort of make a model of Virat Kohli's runs, okay? So we have a data of Virat Kohli's runs. Okay, say R1, the run 1 on the first day, run 2, okay, run n say. We have the data. Try to visualize it, just the runs, okay? The second stuff will be what? The second stuff will be modeling the data by some probability distribution, fit some probability distribution. If you don't fit a probability distribution, it will be non-parametric in nature. Okay, that is not a discussion of our whole syllabus. So we will always assume it fits some probability distribution. Okay, good fitting should be sort of, I was thinking of trying to do that, but it's not really working out. So maybe it's like, so usually like the whole fitting, mostly it is 0 and towards the lower score, it will look like this. Virat Kohli score, let me check once if I have done it. Virat Kohli score looks like this, I guess. Yeah. So this bump is on 50. Okay, and this bump is on 100. It looks like this, and there's a bump like this. So essentially, we can sort of do it by 3 normals mixture, but we will not do it that way. We will sort of making a general estimate, probability distribution estimation like this, maybe. Okay. So it was like maybe I don't know, maybe exponential or point show. Exponential is not a good idea. Point show may be a good thing. Okay, it's a count rate. So point show is a good idea maybe. So yeah, so sort of you can I mean I'm just point show geometric, not geometric, but yeah, point show maybe. So from this point show, if you sort of assume that Ri follows point show some lambda, right? So from this data, say 23, 29, 53, 71, say 103, and then whatever, 20, 19. Okay. From this data, we also want to predict the distribution of it. Now the next step is want to predict the distribution. Predict the estimate of lambda. Okay. So what we will do discuss now, we will discuss I gave an example already. I will discuss now the method of moments method. Method of moments, okay? How do we do the method of moments, guys? Not truncated and normal, really. It can be modeled as a mixture of normals. Okay, I'm not sure about it. I should actually explain with it and not tell you false stuff. I gave an example. Okay, so since this is like live, I should not tell the wrong stuff. It's like a sort of a done for like demonstration purposes. That's a disclaimer part. Okay, so method of moments. It's really simple, guys. Method of moments. It's very natural. What is the method of moments? So Poisson lambda का क्या है? Poisson lambda का lambda is what? Suppose x follows Poisson lambda, then expectation of x is what? The mean of x is lambda, right? So what we do? So the idea is that we connect the moments. So we have a distribution, right? So we connect. The idea is that the key term is that we equate moments of the distribution and the sample moments. We equate that. Okay, for example, here what we will do, we will equate lambda equal to, since it's the expectation, it's the x bar, the sample mean. The population moments, essentially we equate population moments equal to sample. This is a simple algorithm, okay? So it is a very simple algorithm, but whether this algorithm is good or not, that's a very different idea. But it's an algorithm. So today we will discuss about these algorithms. How can we do this with the algorithms? Yeah. Okay. So this gives that lambda is equal to x bar is a good estimate. Okay. All of you understood this algorithm? Simple stuff algorithm. Any doubts? Okay. ठीक है. ठीक है. So what's next? The next idea is that we will do it for normal distribution. Okay. So now essentially observe that the whole problem boils down to studying about probability distributions. Okay, why only first moment? Because okay, we could have done it for the second moment also. Yeah. So the variance is also be order of the moments. Okay. So if we do it by second moment, it would be much more computationally extensive. That's why we didn't do it. Okay, that's the reason. No. Yeah, sort of. Yeah, we should have do the first moment के लिए first parameter के लिए first moment. Two parameters के लिए two moment. The first two moments, variance and the expectation of the variance. Okay, but yeah, I mean, what he's telling is this, that variance of x is also lambda, right? So we could have done that standard deviation lambda is equal to standard deviations of x size. That would have made sense, but observe that this doesn't make sense if you take only one sample, right? Therefore, mean is a better solution. So it doesn't make sense. I mean, a lambda note, nice question, note, lambda equal to variance of x doesn't make sense in case of one sample. For example, the cricket board selector want to select Virat Kohli based on his one data, and he sees that the variance is 0 always, so he will never be get selected, right, Hemant? So that's why it's not a good estimate. I mean, to do variance in that sort of sense, because the variance will always be 0 of the sample. There's only one estimate. Okay. Okay. So now what? Observe that, very carefully observe that we have therefore reduced down the problem to finding estimates, reduced down to find estimates of parameters of probability distribution. Okay? Yeah, we will come to that more. We will come to that soon. Okay, Naresh. So therefore, we will do it one by one. So we have done it for method of moments. So we will give it by for homework lots of things, and we will do it for few things in class. Method of moments. Remember what are all the distributions? Remember, I did it on the first day. So discrete में क्या क्या है, and continuous में क्या क्या है? बोलो बोलो. Discrete में क्या है? We have uniform. Discrete uniform. We have Poinshaw, lambda. We have Bernoulli P. We have binomial n comma p. We have what else? We have geometric p. We have negative binomial p n p m n p, I guess. We are hypergeometric. Okay? Yes. So we try to find out all the method of moments MOM estimators for this. We will do a few here. Okay? To demonstrate the algorithm of how to find the estimates. The next part is maximum likelihood estimate. That is okay. Not the maximum likelihood, sorry. Discrete part, and then the continuous part will come. The continuous part follows the continuous part follows contains rather. One second. Yeah. First is uniform भी है. Uniform A comma B rather. And then is normal mu comma sigma square. Yes. Normal mu comma sigma square. We have other things as क्या क्या है? I'm forgetting so much. Exponential lambda. We have gamma distribution n comma lambda. We have chi-square. What else we have? Beta distribution hai. We have A comma B. Okay. And these stuffs. Anything else I missed? No, I guess. So what we will do is we will apply these algorithms, the method of moments and then the MLE to find. Now these T distributions are really bad. Okay, don't try to deal with them. Devargo. Those are good for sampling stuff. Okay, not for understanding the MLE. So now we will see how to calculate the method of moments. Okay, the method of moments we will see as it will reduce down to some finding some solving some equations. Okay, so it will be an equation solving part, and the MLE we will see it will reduce down to a minimization optimization problem. Okay, so we have an EM algorithm with that. In this semester we have an extension of EM algorithm idea is the MM algorithm, but we will not do this stuff. Okay, I'm just telling you the whole future prospect of it. Okay, so let's calculate it for one by one for each of the. So we have done it for point show. Okay, we have done it for point show, and then we will do it for now. I'm just explaining the algorithms, okay, nothing else. Then I will do the goodness of the whole thing, the goodness of the estimators. Today I'm doing the algorithm. Tomorrow, next day, I will do the goodness of the estimators, okay? So like, let's do the normal distribution part by the method of moments. Okay, this is the normal distribution part. I hope all of you can see it. Can you see the normal distribution part? So we are discussing about the algorithm. So this is the normal distribution part. So observe that the first there are two parameters, right? It's normal mu comma sigma square. Mu one is the first moment. That is a mu. The mu two is the second moment. Expression of x square, which is mu square plus sigma square. Okay. So now mu one. So sigma mu is equal to mu one and sigma square is equal to mu two minus mu one. So sigma hat square is the sample variance. That is this, right? And mu hat is equal to x bar. Okay. So that's the idea. We get the four estimates out here. The two estimates out here. Very simply. Okay, any doubts? It's very simple, guys. Okay, what's next? What's next? Let's see. Let's see. Gamma distribution. Okay, let's do the gamma distribution. One second. Okay. Let's do a problem. Okay. Let's do a real life problem that can come in IIT Jam and ISI. One second, just. Okay. So your homework is to create the set of all method of moments like estimates for each of these, okay? And some problems, so even problems came from this method of moments in ISI GRF, okay? So similar problems can come. Okay, let's do this different problem. No, don't think about those. Don't think about those. What is the sample variance, Gagandeep? Sample variance is simple. You have x1, x2, x6 data. And sample variance is what? Summation of xi square 1 by n summation xi square minus x bar. The sample variance is 1 by n. That will come later on. Okay, that will come later on. Don't think about those. That is to make it unbiased. Okay. Now, let's do this angle theta. So let's do this problem. So your homework is to do all of this and get back to me. Okay. Some problem will be hard. For example, in case of binomial, you will see it will become a little bit hard from. So do all of this and we will make a list of it. Okay. So that you get to practice it. So make a list of it and please share it in the group, our group, and we will understand it from there. Okay. I hope all of you understood the algorithm and then we can discuss those problems again. Okay. If you have doubts. So what I will focus on now, what problems rather come in the exam is the following. Is they will give a random distribution like this. Okay. And they will ask you and the method of moments estimate. MOM estimate. Okay, not only MOM, we will see other estimates also. But MOM estimates is really easy. Just have to calculate the mean stuff. Okay. Okay, Sahiti and Shayu are understanding, guys. You are not replying any here. I hope you're understanding. Okay. So how will you find the method of do this problem for and think about this for a few minutes? How will you do this problem? Think about it. I will give you some countdown. Take down the problem. I will give you some countdown, guys. Okay, any ideas? Okay, write down the problem. I will send it in the group. Do you want me to send it in the group? I have sent it in the group. Yeah, perfect. We need to find the mean. So what is the algorithm? Find the population mean and equate to the sample mean. Simple. The sample mean, you know, it's x bar, right? So first take down the mean. First do the mean. So first step is find the mean of the population. Find the mean of the population. Okay, I really want you to do all the corresponding estimates of all the distributions, okay? Because next day, when we will start about understanding whether parameter the estimates are good or not, I will ask and randomly pick up guys from like people and ask you to give me the estimates. So discuss in the group by today or this week and make a list of the estimates so that you can give me at that time only, okay? This answer. And we can find the expected value and all the stuff very easily. Okay? So you need that. Now we'll see the probability prowess. You need to understand all this stuff. Okay? Okay, find the mean. I will give another countdown to you. Richa, are you understanding? Acha, Richa and Debargo, who are from math background, are you understanding since it's your first formal introduction to statistics? Are you facing any issues with the philosophy of statistics? As you will say, everything is revolving around the probability, okay? So, okay, so any ideas, guys? A lot of time went away. So let's try to find out this the mean of it. The mean of this distribution. It's really simple. What is the mean? Mean of the density is what? Can someone tell me? How to calculate the mean? You should understand how to calculate the mean. So which is the parameter over here? The parameter is alpha, right? We need to find the alpha parameter. So what is the parameter? Let's try to understand it. So we will find the expectation. Expectation of x is what? It's integration. It's the expected value of cos theta rather, okay? It's integration minus 1 to 1 plus alpha x by 2 times x dx. ठीक है? So what do you get out of here? You get, so calculate this. Yeah, we get mu is equal to alpha by 3. All of you get this, got this, guys? It's very simple. Mu is equal to alpha by expectation of x is equal to alpha by 3. All of you got this? There is no change of variables. No, Gagandeep. They told that instead of taking theta, we have taken cos theta, okay? We have to find the expectation in terms of x only. X will cancel out. It's not a very big issue. What will remain is the alpha. We need to find the estimate of alpha, not the theta. Theta is the random variable over here. And it's given, the density is given. When density is given in terms of x, just find it in terms of x. Simple. So since the expression mu is equal to alpha by 3, we equate mu alpha by 3 to x bar. So what do we get? We get alpha equal to 3x. What is a good estimate of the distribution? So the actual distribution will be fx. For the estimated distribution will be fx is equal to alpha hat is equal to 1 plus alpha hat by 2. Where alpha hat is equal to 3x bar from the data. So this is the estimated distribution that we have got. And we will assume this and then we will move ahead. Yeah, expression of x given alpha. This given is not a very big thing. It's a big thing when you will do see a bit of Bayesian inference if we have time after IIT. Okay, all of you understood. Shadul understood. Sahiti understood. Sahiti is not replying. I hope I think she has left. Let me message her on WhatsApp. Okay, any doubts, guys? Then we will move on to the MLE estimates. Okay, but remember your homework, guys. List out all the MOM estimate, the method of moments estimate of all the distributions, normal distributions you have. Okay, and you will face problems over there. Okay, so since there are some problems with the YouTube part, no, you don't remember that, Gagan. That is for the part of that is for your own sort of practice with MOM. Okay, it doesn't make sense to teach you guys how to do integration and then do it and solve equations, right? So that's a homework I give you. I'm here to give you ideas and share how the algorithms and do the main thing. So MOM is not the main thing. I will tell you what to do after the MOM. That will come in the next class. So today the class is all about algorithms and discussing the algorithms to get to the estimates. Next day's class is about understanding these estimates are good or not. We'll give some various ideas to give the estimates whether they are good or not. Okay, that's the idea. Okay, by the way, since people are lagging behind in this chats, if you have any doubts, the suggested part is that you see the video, YouTube video from PC and your laptop and you reply me in WhatsApp if you have any doubts. Okay, I will surely answer that in that moment. Okay. ठीक है. I am moving on to the MLE now. MLE is much more interesting and much more accurate. MLE is a really beautiful thing. I love this idea totally. ठीक है. Remember the homework, I guess. So do the homework. The homework is really important for you. Okay. I love Emily, okay? Emily is okay. So let me tell you a bit of history of Emily. So Emily is the first. So, you know who discovered Emily, guys? Who discovered Emily? Do you know? Fisher, right? It's Fisher, okay? Who discovered the Emily? Can you see the name, all of you? Yeah. Sare Fisher is one of the most influential statistician in the history of statistics, okay? And what did he do? What did he contribute? So it's called Fisherian statistics. So its whole name is Ronald Fisher. And who is Fisher? Fisher was a guy, and he looked really not and handsome he is. So I'm going to share because he's one of my favorite statisticians. So here is Fisher, and R. Fisher was an English statistician, and what he did was he gave the idea of the maximum likelihood estimator. Okay, his whole idea was to like he developed the idea of Fisherian statistics. What is Fisherian statistics? Is the algorithm based statistics. Okay, the whole algorithm based statistics, and he gave the idea this maximum likelihood estimator, and from there he like developed the whole theory of statistics. Okay, and yeah, Fisher is the father of that stats inference, and you can see him live over here. I really love this sort of ideas in I didn't know this. I discovered this today, so I'm experimenting with it. I hope you're enjoying this new animation and stuff like this. So that's the idea anyways. So let's hide Fisher over here. And okay, so what's next? So this Fisher moved ahead to make the maximum likely estimates, and then he gave various other stuff over there. And what we will understand that this Fisher is sort of the creator of this algorithmic aspect, okay? The algorithmic aspect, and then understanding whether it's good or not. Okay, he has developed something called Fisher information and other lot of interesting stuff. So it just deals with this. We have a data, we have a probability distribution, we have parameters, we have an algorithm to estimate the parameters, and then we have a mathematical framework to understand whether the estimates are good or not. Okay, this is a simple idea. Okay, this is the estimation theory part, and the testing hypothesis part take help of estimation theory to understand and do other stuff. This is a point estimation and the interval estimation mostly. Okay, okay. So let's side him up a bit. Let him watch us do mathematics, and let him watch us do mathematics and statistics. He came to this idea naturally. See, that time was the age of probability. Okay, so he came to it very naturally. That's really natural. I mean, you will see how natural it is. So what is MLE? So MLE, the full form here is maximum likelihood estimate. Okay, let me give an example, guys. This is the most important part of the whole statistics you will be doing in this whole preparation part. Okay, so please be focused on this. The maximum likelihood estimate. The maximum likelihood estimates focuses on rather God, Gagandeep. Okay, he's on fire. Nice. That was really good. Okay. So what is maximum likely estimator? The name suggests it's something to do with maximum. And it's something to do with likelihood, and obviously it's estimating something. So it's like this. It's very simple. So okay, let me give an example. Um. Okay. Okay. Just wait a minute. Just wait a minute. I will give you a real life example that is happening right now. Okay. Okay. Tell me a good restaurant. Let's say Chow Man, or let's say Science City, or in Kolkata. I will give you a Google data. Oops, it's not giving here Google data anymore. Okay, yours is what is a good chow man say? Good restaurant. Chow man, chow man. Google is not giving the data. Remember, Google gives the data of whole how much that sort of traffic is. Remember, can you give an remember how much the traffic in a certain place? I will tell you. I will give an example, real life example. How much traffic in a place? Traffic, chow man restaurant, traffic data. अभी दिया. See, ठीक है. Let me give a real life example over here from Google only. ठीक है. So now it's COVID time, and this is I took from the picture from Google. So all of you can see the board, guys. So I gave an example of what is a popular time in a particular restaurant. The restaurant is Shawman. It's in Kolkata. Okay, and yeah, I'm not looking up his life. I am just looking up. Okay. So, okay, so understand very carefully. Suppose you're in COVID situation and you're hungry and you're sort of seeing this data, okay, from Google that where to visit, which is the best time to visit, okay. You will obviously look for less sort of or maybe what is the best time to visit this region of a visitor restaurant. You want to look at it, okay. So there's a distribution sort of the visiting probability distribution. It's sort of like this. There are two normal distributions like this and sort of like this. Okay. So suppose you want to understand which is the highest. So the data is that x is the time of visit. Naturally, there are two times, right? Naturally, there are two maximas of probability distribution. So the time of visit to this restaurant. So you can see from the data there are sort of two times. One is at the lunch time, and one is at the dinner time. Suppose I ask you that the time of visit to the restaurant at dinner time it is. Okay. Now, how will you give the estimate? What estimate will you give? Which is the best estimate you will give? Tell me. What is your favorite estimate that you will give over here? Or let's say I ask you about the X is the dinner. So D is the dinner time and L is the lunch time. The best where the popular lunch time rather. Tell me which is your favorite estimate. What will you give? What will you give? No, I'm asking that. See. Yes, perfect, Gagan. That's the idea. That's the idea. So sort of You can understand from here. I will rub it off here again. So this is sort of the idea of these are the lunchtime data and these are dinner time data. Suppose the dinner time data, you sort of tell the maximum time and the best estimate is this around this region. 6, 7, 8, 9. So around this region, okay? 7, 7:38 around this region. And the maximum, the popular region is this. Around this region, right? So that's the idea. Okay. So the distribution of the time where it's visits is this. The density of people who visits. So it's the 2 p.m.ish region, okay? So therefore, what we are trying to look that sort of the mean of it, okay? Suppose this is a normal distribution. So you sort of assume the lunch follows normal mu comma, say sort of what? 1 hour, okay? Mu comma 1. So what is this mu? What is this estimate of mu? The estimate of mu sort of see that, okay, the estimate of mu is where the mu is the largest, mu hat is the largest, okay? So this is a mu. Okay, but this is not an exact definition of the maximum likely estimator. I'm just giving an example where it's becoming the maximum, okay? Sort of the 2 p.m., right? 2 p.m. is the mu. So that looks like it. So how to formally define it? So how to formally define it? Let's try to understand this. So we have x1, x2, like this is a mathematical formulation. We have x1, x2, xn as the data. Okay. Let's say it follows f of theta. Okay. So now our aim is estimate this theta. So what is the philosophy? Philosophy is very simple. Take all possible thetas. Take all possible thetas. Okay. Theta can vary from anywhere to anywhere. Okay. Now, what is the likelihood? We will compute the probability. So take all possible theta. So the first step is that step 1. Fix a theta. Step 2. Find the likelihood L of theta given data. What is the likelihood? That probability that xi, probability of theta, probability of theta of x1, joint distribution of this. Okay. All these data together. It sort of means that what is the given this theta, what is the probability it has come from this? Like given the theta, what is the probability of this data? Given theta, what is the probability of data? What is the probability of occurrence of this data? Okay, given this theta. Now, what we will get? We will have got L theta. Now, L theta is a function of theta, right? Is a function of theta. What does it tell? It tells you that what is the probability it has occurred at various times, right? So now what will you check? Which theta will you take? Which theta will you select? You will select that theta for which the probability is largest, because, so let's take an example. Suppose for theta 1, you have got probability of data, of given data coming from f of 1, that is theta is equal to 1, is equal to say 0.3. Now for theta equal to 2, you get probability of given data coming from f theta equal to 2 is 0.8. given data. Now, which is the most likeliest value of theta? It is 2, right? It is 2, right? Yes. All of you understanding this philosophy? It is 2, right? Most likeliest value of theta. It's sort of like this. So, so it is like this. So we have lots of. So I am asking you. I am telling you. For example, let's give an example, real life example. Yes, that's the idea. So what is the idea is that suppose you have various thetas and we have got a various values of probability based on theta. Okay. Now, what is the probability? Likelihood. Likelihood means that the probability of occurrence of the given data given that theta. Okay. For theta equal to 1, we are seeing the probability actually the data has occurred from that f of theta equal to 1. F of theta equal to 1. Okay, for various theta, we are computing the probability. What is the probability? The probability means, so what is the maximum likely estimate? We are sort of taking the likelihood which will maximize the, so we are taking the estimate which will maximize the likelihood. So what is the meaning of this? The meaning of this is that MLE means we are sort of taking the likelihood we are taking the estimate, sorry, which maximizes the likelihood. Estimate which maximizes the likelihood. Estimate of theta which maximizes the likelihood of occurrence of the data. Okay, this is the entire idea. All of you understood? Any doubts, guys? Any doubts? Is there any doubts? Okay, good. ML is really beautiful. It's really beautiful. It's really intuitive. That's a beautiful idea. Okay, I am seeing there's some private option, private chat option. Okay, do you know how to do private chat? In here, I am not really sure about it. Okay. Okay, that's a maximum like so. Sahiti and Shariul, did you understand? Richa, did you understand? Raj and others. Yeah, we will discuss this in details. For multiple parameters, we will maximize the likelihood of all the parameters, the likelihood of the data given the parameters. Okay. So we will maximize the likelihood that L of theta. So what we will do, the fifth step is we will take theta hat is equal to that value which maximizes L of theta. Okay. This is algorithm, guys. This is algorithm. Schedule, you understood schedule? And then what's next? So we will take an examples now. So I have just explained the algorithm, guys. Okay. Now the next part is about examples. So let's do the examples. So let me share the ways out. So what is likelihood? Likelihood is this. Okay. And then if the exercise are as you do the IID, if the data is IID, then we will get Yeah, I will tell you. Okay, we will now ask. So observe if xi is an IID, we get that likelihood is product of the fx, the product of the distributions. Okay, the corresponding xi's. Okay, and then now what we want is the to maximize this. So for example, if you see that often these things are in terms of exponential, okay, so we will need log. I will tell you why this exponential comes up, because these people have started with something called exponential family of distributions, okay. That's why this law has become very phenomenal in this approach, but it may not be important. Exponential family, this is not in the syllabus, but okay, it's good to remember. So all these good distributions that you are seeing, they can be modeled by something. They are all in exponential family, okay, something called exponential family. Okay, anyways, so let's not go here. Let's try to see the whole aspect over here step by step. So we have got the first step, the second step, likelihood, and L of theta. Now the fourth will maximize it. Okay, how to maximize it? We'll just maximize this by doing del L del theta. Del theta equal to 0 for multiple parameters. For multiple parameters, we will do what? We will do partial differentiations. And we will get various equations, so we will equate that equation. So we will take an example for normal only, okay? Okay, any doubts? Oh, this will not if it is not independent, we cannot really work with it, okay? We assume the data to be independent and IIDs. Okay? So this is a whole mathematical algorithm now. Now we will just take examples. Let's take examples. So let's do it for point show. Suppose it's point show over here. So this is the distribution of point show. Let's do it for point show. So we'll do it for point show now. So point show distribution is given over here. We have lots of point show distribution given over here. Not lots of, only one. Okay, so this is a point show. Now what's the next step? We have the data x1, x2, xn. We will now form the likelihood. Okay, xi IID point show. Okay, it's an assumption. Xi IID point show lambda. Next step is what? We will form the log likelihood. Okay, so before that, let's write the likelihood. That is L of theta. L of lambda, say. L of lambda is what? It's probability x1 is equal to x1, x2 is equal to x1. These are realizations, small xi's, and the big xi's are the random variables. It's equal to what? Product of I from 1 to n. What? Probability of xi is equal to xi. That is equal to product of I from 1 to n, lambda to the power xi, e to the power minus lambda by xi factorial. Okay. And if you get this now, let's calculate the log likelihood L of lambda. We calculate the L of lambda. Let's see the L of lambda over here. Here is L of lambda. It's coming. So L of lambda is. So observe that take a log of it. If you take a log of it, obviously this is a big xi. Okay, you can take it smaller, whatever. It doesn't matter. Okay, to make it a random variable, you must like big xi. If you just make it, it should be taken as a random variable because the samples are random variable. So if you take LXI, observe that log will become summation. So xi log lambda minus log xi factorial. So it will sum up as log lambda common xi minus n lambda minus summation of log xi. All of you understood this? No, IID random variables is the assumption of the sample, random sample that is called. Yeah, essentially all models are useful, but all models are wrong, but some are useful. It's essentially true, right? Because models are just illusions. The real thing lies in the population. We are just estimating the populations. It's like the population is the cosmos or the if you believe if you are sincere in his project, you should not believe in God. You should believe in nature or the cosmos. If you believe in God, then the population is the God, and we are just trying to perceive the God by our senses. Okay, so that's the idea. So that's why we are taking samples from the world. Okay. Anyways, all of you understood this. Let's move back and let's see how to do. Now, do we need to? That it's time for the derivative now. Let's do del L, not del, d theta, dl lambda. dl lambda. Again, I do this mistake. Okay. Let's derive this. So it will become 1 by lambda summation of xi minus n lambda. ठीक है. Okay, minus n it will be, sorry. Minus 0. Okay, it will be equal to 0. It implies that sorry, lambda mle hat is equal to x bar. Observe this is same as the method of moments likelihood. Note is same as MOM likelihood. MOM estimate, sorry. Now there are two questions to you today. First, the homework is, list all MOM estimate. Okay, the homework 1, the homework 2 is list all MLE estimate of those distributions. And you will see a lot in common. And I will present you with a research problem. Is that when is MOM estimate equal to a MLE estimate? Okay, that's the question today. It's a research question. You cannot think of it research question. There's a solution to it, but you can sort of understand. It's really beautiful solution. It's a given under a given condition. So this is the idea. Okay. Yeah, so sample may or may not be so it's an assumption, Gagandeep, okay? If you don't assume that assumption, that's why we are machine learning other stuffs to make use of it. That's why statistics is based on mathematics. So people try to understand statistics with easy assumptions, okay? Since it's based on mathematics, but mathematics cannot really go beyond much. That's why it is taking time to build the mathematical foundations of machine learning and deep learning and all this stuff, algorithms. It's easy to give algorithms and get results and do cross-validation and checks, and whether it's good on training sample and test sample and check whether various other things, okay? it's doing validation and validation. So there are a lot of algorithms to do it. Okay, but the idea when we want to do it mathematically easier way out, it's not really easy in that sense. Therefore, we need to impose upon restrictions and see the basics part. Okay, to see do the simple part rather. Okay, that's why there are various algorithms nowadays. Okay, all of you understood this? Oh, there is a condition. Yeah, that's a condition you have to find, Gagandeep. This is a question I asked in my second sem of first year when I really learned and saw that method of moments and MLE estimates are really equal. I got the answer at the end of BStat third year. Okay, there is no such stuff over there, but I sort of researched it and got it. Okay, from various other places and tried to understand it myself. So that's why it's a research question to you guys. Okay, it's really interesting when you will see we do different algorithms give the same estimate mathematically. Okay, that's the idea. ठीक है चलो so I will end today's class by the normal estimates. Okay, and your homework will be getting the list of all these estimates and get back to me so that next day we will understand the goodness of the estimates. Okay, and we will understand the estimates how good they are. Okay, and then we will follow that. So there are two type of questions that come in MLE and MOM. First is that they will give you random distributions and they will ask you to do MLE and MOM. Okay, that's the simple stuff. And yeah, that's it. So they will give you random distributions and they will ask you to do MOM and MLE. That's one type of question that will come, or sort of problems. Another type of problem is come, they will ask you to give and test and understand good estimates, the sufficiency and whether so we will do the next day. So today's discussion will be understanding the algorithms. Okay, I hope you understood the whole thing. Okay, so today I will discuss two things. Let's do the normal part and let's do the uniform. The uniform is really important. Okay. ठीक है चलो so let's do the normal part first. By the way, I want to show you the graph of the point show how it looks like. For a certain data, the graph will look like this. Okay, and therefore which one you select the this one. This is the lambda estimate you get, sort of. It's for some particular data where it get maximized. So therefore there have been various algorithms, so there have been ideas of maximizing this. There has been in ML terms there is gradient descent method to find the maximum. Okay, there is EM algorithm method. There is MM algorithm method. Okay, MM algorithm is something I'm learning this semester. That's why I told you. Okay, so I am just trying to make you as much knowledgeable as possible. Okay, anyways, so that's the idea. So let's do the normal part. Regarding the Bayesian inference part, let's see how you really understand statistics, guys. I will test your knowledge and then I will go into advanced stuff. I may even do AM algorithm, MMN algorithm if you're really good with it. Okay, but we will do basic Bayesian inference. Yeah, we will do basic Bayesian inference. It's important to but we will do this after IIT Jam because IIT Jam is really near and this year we have already lost time, so we will not waste our time using this basic this advanced stuff. Okay, so we'll do this after ISI when we have a lot of time and you have the time to expand your knowledge. Okay, yeah, we will we don't have EM algorithm. We will discuss those if if you want after some extra classes, or I will make some videos on it. That's not a very big deal. Okay, okay, chalo. So the normal part, let me do the normal one. So the normal one, let me write the. So we'll do the normal distribution now. The normal distribution will be 1 by 2 Do the homework, guys. It's really important. I do not stress upon the homeworks very much, but at this time I'm doing it. And now go to the problem repository if you're a student of Cheenta, and you can attempt the MLE and the MOM quizzes, okay? The problems, I think. You're just one class away from the whole thing. See, this is the idea. That's why I have focused so much on making your probability so good that you don't face any problem later on. If you don't know probability, this whole thing will take time, at least 5-6 days to understand. But since the probability is really good now, it's only taking 1.5 hours to understand this very easy stuff. It's difficult, but you're understanding because the probability is good. That's why I focus so much on your probability basics, okay? You should understand this that way. So probability is a basic, okay? So yeah. Anyways, so normal distribution. The first step is that this is the distribution. So all of you understood it, I guess. This is the density of normal, and this is the xi ke liye, the product, because it's just distributing, okay? And then the next step is finding the likelihood, right? Let's find the likelihood. So this is the likelihood over here. We will find the log likelihood directly. So log likelihood, since it's in product form now, it's easy to do log likelihood. That's why people do log likelihood directly without cap. So essentially, this is sort of the likelihood. Essentially, this is likelihood, okay? So if you do log likelihood, what you get? You get log of this minus. So this comes as a constant. Okay, this doesn't come as a constant. I'm so sorry. This comes as I'm doing something wrong, I guess. Oh no, this is actually what? This is lambda to the sigma to the power minus n times some constant to the power n times exponential minus that thing. So this my sigma to the power minus n comes minus n log sigma. This constant will be there. We are not really interested in the constant part because after differentiating it will go away. And this n by 2. Yeah, this is the constant part. That this will not be the interesting part. Okay, this will go away soon. This is not really interesting. I mean, this will be there, but it's not really interesting. Not important. And see this part. So minus sigma, if you do remove the exponential, log is there. So it's minus 2 sigma square summation of, yes, summation, because it will be exponential minus half summation of xi minus mu this thing, okay? So that's why it's cancelling out. Okay, so you get this mu. Now you just need to do the derivative over here. So if you do the derivative, what will you get? To the derivative, you will get the following over here. This is the derivative. If you do this derivative with respect to mu, you will get this will be not there, it will be 0. This will be turning out to be summation of twice of this. Okay, twice will get cancelled, 1 by sigma square. So this is the idea. And minus will get plus. And if you do sigma, it will be minus 1 by, yeah, perfect. And it will be minus sigma cube, yeah. So this will come up. Okay, if you just do the derivative of this. Now do it to 0 and do it to 0. So what you get from here, you get that the sigma square will go to 0 side. So it will be mu hat MLE will be what? It will be x bar. Okay. It will be n. So essentially it's n mu is equal to summation of xi. So mu is equal to x bar, mu hat. And here it is mu hat is equal to x bar. So what you get from here? You get minus n sigma square is equal to summation of xi minus mu whole square. Okay. I'm sorry. And you get from here that sigma square hat is equal to, it will be minus 1 by n summation of xi minus mu whole square. Okay. Now this will be mu hat, so it will be mu hat whole square, that is 1 by n summation of xi minus x bar whole square. Okay. So some homework from here. Remember the homeworks. So observe one thing. So now instead of this mu, what you assume that x1, x2, xn follows normal mu naught comma x sigma square. That is mu naught is known, okay? If mu naught is known, then this is a constant, right? Then you will see it will turn out, sigma hat will turn out to be, in this case, 1 by n summation of xi minus mu naught whole square, not x bar. Okay. So this is a beautiful idea that you are using all the ideas over here, okay? Try to understand this very carefully. This is really important to do this problem. And what else? Yeah, nothing else. Yeah, the homework is do all the ML. Anything else? No. All of you understood this? Any doubts? Any doubts, guys? I forgot another problem. Another really important problem is that prove that MLE of f of theta is same as f of MLE of theta. F is a continuous function. These are really important idea. Using this, you can sort of see, observe what we have got. We have got a sigma square hat sigma square ka MLE, okay, not sigma ka MLE. From here, you can actually tell that sigma hat ka MLE will be root over this, okay, by this sort of theorem. So prove this one. Okay, this is really important to make. It's okay. Okay, Sahiti and Sharif, are you understanding, guys? Any doubts? Okay, last problem for today. We are already over time, but we will still do this. Okay, the uniform, because uniform is a bit different and not derivative of the question. Okay, one second. One second, guys. I think I need to do the uniform over here. ठीक है, uniform वाला कर दो. It seems that the statistics syllabus is really less, or maybe you are really good in understanding the whole thing. No, I will not give the proof now. You do it, I will give the proof later on. It's really easy, not really hard, Gagandip. Do all the homework. This is the most important class in the history of your statistics course in Cheenta, okay? It's the most important and the most beautiful class, I believe. So do all the homeworks as I have told. If you do the homeworks as I have told, I'm sure no one can catch you up in the statistics. Your basics will be really crystal clear, okay? In statistics. This is a basic class of statistics, okay? That's why I think it's important. Okay, so I will end the class today by the uniform distribution example. Okay, let me take a rest for a few minutes. My voice is a bit down. Okay. In the meantime, okay. ठीक है. Yeah, the first I'm giving very homeworks. but I think it's really important for you. Okay, the uniform was a stuff x1, x2, xn follows uniform 0, comma theta. So what is the MLE of theta? This is the most important question that you usually face. So as I have told, there is one type of idea is that is one is the one sort of estimate we have got. Let me revise. I will revise today. One estimate we have got a method of moments. The least square estimate in the corresponding framework of the regression stuff. We have got. Oh, I need to show this problem too. That MLE in regression is same as OLS in regression. Okay, I will show this today also. Okay, today class gonna be a bit long. Anyways, but because I'm excited today. Okay, so the log likelihood L of theta is what? It's f of xi. Okay, probability of f of xi. I mean the product. And it is what? What is f of xi, guys? It's really simple. It's what? It's equal to 1 by theta. But remember, xi must be less than equal to theta and greater than equal to 0. So essentially it's 1 by theta indicator into an indicator function. It's an indicator that xi are less than equal to theta. It's a sort of remembrance, sort of tagging it at all the random variables are less than theta. Okay, so that is what it's coming out that therefore it's coming out it's same as 1 by theta to the power n into an indicator in product of indicators that xi less than equal to theta. Now product of indicators is less than xi equal less than equal to theta is what? That means it's indicating that all the xi's are less than equal to theta. Prove that in your homework that this is same as indicator. The maximum of all of them is less than equal to theta. The orders, the largest order statistic that we have done in the last class. Oh no! Why are I doing the advertisement with the existing customers? Because because I will make this not in public mode. I will share it to the people because people are telling me to make some videos on estimation. But I think this estimation video went really good. So the class. So therefore, I will share it with the people out there. That's why I'm making some advertisement. That's a really good question, though. Yeah. Okay. So regarding this part. Okay. So therefore, observe if indicator all the xi's are less than equal to theta, it's same as the maxima of all of them are less than equal to theta. Okay. So therefore, what we get over here, hi Prachi, when did you join the class? You are not replying. So therefore, it's the indicator 1 by 3 to the power n into indicator xn less than equal to theta, the max order, largest order statistic. So therefore, what do we get? We get that this is the L of theta. Okay, it's really simple now. Now what's next? We will plot the L of theta. We cannot do the derivative, okay, with this term. So let's plot this L of theta. It's L of theta and this is theta over here. So observe that 1 by theta to the power n is a decreasing function, right? Like this. But this theta is greater than equal to xn. That is, xn is here, says a point. Is theta is a theta, xn is a point, right? If from the data, suppose 1, 2, 3, 4, 5, this is x of largest of statistic is 5, right? So it's a point, it's a real number. So xn is greater than theta, therefore it's 0, 0 before xn. Like this. Okay? And therefore it's decreasing. Now while L of theta is maximum, L of theta is maximum in this region, therefore. That is, the MLE of theta hat is equal to the largest order statistic. And it makes sense, now. Try to understand this in a very intuitive sense. So we have a data from uniform 0, theta. Say 1.1, 0.3, 0.2, 9.3, 8.5. Okay. So from this, what you can get the max, that what is this theta? This theta is a sort of, we are taking numbers uniformly from 0 to theta, right? So what is a good estimate of theta? It should be the maximum, right? Or maximum 9.3. It should be the maximum, right? Because that is the part that one can go closest to the theta in terms of the sample. That's why the larger our statistics sort of makes sense in terms of the estimate. That is the MLA. That's the most probable idea. That's why larger statistics makes sense. Okay. Okay, Prachi, I hope you understood everything over here today. Okay, all of you understood this example? Why uniform ke liye this is largest of statistics is the MLE? Okay, good, nice. Okay, I think I will do the next part. I hope you got it scheduled too. The next day, what I will do is that I will start with the MLE part, okay? Because that's always sort of a revision. So next day, I will start the class with getting to you that, with telling you rather what is the MLE and why the MLE in regression is same as the corresponding OLS estimates in regression, linear regression, where the sort of the connection is normal, where the data follows normal, okay? Otherwise, it will not happen. Yeah, that's what I told Gagandeep. MOM and MLE can be equal in some sense, and we will compare. So the next day will be for starting with these basic ideas of regression stuff. We will sort of revision to, and we will start comparing the estimates on the basis of unbiasedness on MAC and all other stuff, like all other interesting stuff, sufficiency if we get time. So I mean, not tomorrow, but we will surely do this in much more longer details and much more longer format. But I really want the homework from you the next day, okay? Because I will ask you at that time, okay? And it's really easy. It will, I'm sure it will help you out. You will see the connection together. Otherwise, there is no beauty in that, okay? Okay, see you in the next class. Okay? And if you have any doubts, so what are the 4 estimates? The 4 estimates, 4 sort of ways of understanding is method of moments, maximum likelihood estimate, and Bayesian inference, Bayesian estimates. We will not do the Bayesian estimates, but we will do the corresponding idea of we have done the corresponding idea of method of moments and we have done this. So what's next? The next is understanding of this example and each of these corresponding ways of doing that, okay? And then we will see that when the performance and the validation of the estimates, how they are good. So the properties of the estimates. We have unbiasedness, we have consistency. We have a lot of interesting stuff over there, but this stuff requires a probability 4. So that's why probability 4 will be done by Shoham on tomorrow's class. And please do attempt the problems in our problem repository, in our gold course that we have, and all the courses we have, the bronze one. And there you can find lots and lots of problems on this estimation and stuff like this. So please do attempt this. And we'll see you in the next class. And bye-bye. Have a nice night ahead. Okay, any questions, guys, from your end? We have the MSc part, yeah. So we actually compare those two estimates by MSc, guys. Okay, we will do that next day. How to compare this stuff. There are lots of estimates. There is something called UMView estimation, estimate. There is minimax estimation. Lots of different estimates are there. Okay, this whole estimation theory is sort of understanding the estimates of all this, comparing the estimates and all this stuff. Okay, that's the idea. Okay, any doubts, guys? Any doubts, guys? What is it? What is your doubt? Gagandeep, what is your doubt? Okay. Okay, please tell me your doubt in the WhatsApp one-on-one group that you have for your doubt clearing, Gagandeep. And I see you there. Okay. That's what I told na, Gagandeep. We will understand by MSc. It's very specific to problems. Okay. Yeah, this variable, these methods are both for continuous and discrete. Yes, because the likelihood is a yes, these variables are both I have done from one for point show, right, and one for the the corresponding normal, right, which is continuous. So it's MOM or MLE, which is better. It actually related to the corresponding distribution which we do. Okay. So we will do this next day. How to compare two estimates. Okay. So see you and bye bye. Any doubts?